Okay, thanks, Russell. So I plan to do basically PowerPoint for the first half and then Blackboard for the second half. So, but you know, okay. Extractors are motivated by weak random sources. So a weak random source will model as a random variable on, say, n-bit strings. And the most general model of a weak random source is to lower bound the min entropy. So we say that the min entropy x is at least k if the probability of any particular string is at most 2 to the minus k. And intuitively, the worst case example of a source with min entropy k is a flat source. This is where the probability is concentrated on as few strings as possible, namely 2 to the k strings. So that is, we pick some set of size 2 to the k, and we take a uniformly random string from this set and output it. Such sources, weak sources, well, actually, you know what? Maybe I should have done this first. Some examples of sources with min entropy k could be, if you think about the bit representations, right? It could be k uniform bits, and the other bits are functions of these k uniform bits. Or it could be that each bit is a little bit random. So maybe the conditional probability of xi conditioned on the previous bits is somewhere between k over n and 1 minus k over n. And it could be some kind of convex combination of these. OK, let's see. So a weak random source can arise in several different ways. The original motivation was from physical sources of randomness. You can imagine that you want to get good randomness, but it's, your physical source doesn't output high-quality randomness. But another natural way these arise is in cryptography. Say an adversary has some information about a string. Well, if we condition on this information, then the string may still have some min entropy. And an example of this is the bounded storage model. So more specifically, suppose we start with some uniform string x, which is a uniform n-bit string, and some adversary knows some function that maps n bits to s bits. So the adversary has s bits of information about this string. Well, if f is regular, in other words, if f is 2 to the n minus s to 1, then the min entropy of x conditioned on f of x taking any particular value is exactly n minus s. And even if f is not regular, something similar still holds. If we choose I should have said the probability. I should have had the probability over x. So we think of it's correct. OK. So the conditional min entropy of x, given that f of x equals a, when we choose x randomly, is still at least n minus s minus log epsilon inverse, with probability at least 1 minus epsilon. And so these also arise in pseudorandom generators for space-bounded machines in a similar, with a similar idea. Here, instead of conditioning on the adversary's information, we condition on the Turing machine's configuration after some computation. So if the Turing machine is a space S machine, the same situation applies. We have S bits of information about the source. OK, and so this is one reason why extractors are useful. OK, I did this.
Yeah, so for the f is that, suppose f is like some probabilistic thing that gives us a. Does that still hold?
If f is probabilistic, yeah, it should still hold. Yeah.
It might be better if you reveal the random bits used by the probabilistic source, right? By the probabilistic function, then you're in this deterministic situation.
Yeah.
So that's strictly worse
Okay.
as far as information goes.
So our dream goal would be to extract randomness from such sources. So our dream goal would be we have a source with min entropy k on n bits. We'd like to have an extractor which outputs many bits and which gives small statistical error. And here we'll measure statistical error by the statistical distance or the variation distance, which is half the L1 norm. But this is impossible, even if the min entropy is n-1, even if we just want to output one bit. Okay, and the proof of that is simple. Right, if we had some function, mapping n bits to 1 bit, well, that would divide 0, 1 to the n into f divides 0, 1 to the n into f inverse of 0 and f inverse of 1. Now, one of these takes up at least half the strings. The uniform distribution on that set is a source with min entropy n-1, but for which f always outputs a fixed value. Okay, so that's impossible. So instead, there's been a long line of research, and it turns out you can add just a small random seed and achieve what you want. Okay, so an extractor takes as input a weak random source with min entropy k. It takes a short random seed. Think of the seed as about log n random bits. And it outputs, say, almost all the entropy. And let me write let's see, these parameters down. So, OK, so we're going to have an n-bit source. We're going to have a d-bit seed. And we're going to output an m-bit string. So this is the source, seed, and output, just so you remember the notation. OK, so we couldn't hope to output more than k bits. And what this says is that we could output, say, 99% of what we could hope for. And a strong extractor, often we want a somewhat stronger property, which we call a strong extractor, which says that not only is the output close to uniform, but even conditioned on the seed, with high probability, the output is uniform. Or in other words, the ordered pair of the extractor and the seed is close to uniform. Yeah.
Is it clear that the min entropy is the tight condition and it cannot be Shannon entropy? But the min entropy being the right condition for getting k bits, is that?
Yeah, I mean, you could also use the Rényi entropy, but which is the same up to a factor of 2. Yeah, as you said, you cannot use Shannon entropy. Shannon entropy, for example, you could have high Shannon entropy, but let's say you could have a distribution which has Shannon entropy n/2, but with probability half outputs a fixed string, say the string of all zeros. So you can never get probabilities below half in that case. So that's why, essentially, really min entropy is the right thing to look at. Essentially, you're just counting the number of bad strings. So it's, we'll see another way to look at extractors, and you'll see that it seems right. So in this talk, so first I'm going to discuss seeded extractors, which is what I just defined, give some applications and more. And then I'll talk about some seedless extractors for structured sources. So another way to get around this impossibility result is to disallow general sources and instead impose some structure on the sources. So I'll discuss some seedless extractors for algebraic sources, some an application in cryptography, and some complexity theoretic sources. Okay, so one of the first uses of extractors, in fact, predates extractors. This is where they used an extractor with a large seed. So this is due to Bennett, Broussard, and Robert, who looked at the problem of privacy amplification. So here, Alice and Bob share some weakly random string x. This is a weak secret. But they'd like to do cryptography, so a weak secret isn't necessarily good enough. They want a uniform secret, or something close to uniform. Now, they can communicate over a public channel. So in other words, an eavesdropper can overhear everything that they say. So their goal is to convert this weakly shared secret x to a uniform secret. And again, we're going to assume that the adversary has unlimited computation, except that she's passive. She won't change any strings in transit. So here the solution is that Alice will just pick a random seed and send it to Bob, and the shared secret will be the output of the extractor. Okay, and this is correct by the definition of strong extractor. Strong extractor ensures that even conditioned on the seed, the extractor output is close to uniform. So even though the seed is public, the extractor output is close to uniform and known only to Alice and Bob. So that's one application. Another application is pseudorandom generators for space-bounded machines. So this was actually our original motivation for when we defined extractors. And the basic generator, basic idea is to, let's say, you could increase the length of xy by looking at x and then the extractor output of x and y. The extractor output of x and y is longer than just y. And that's why there's a gain here. And why does something like this work? Well, if we condition on the configuration after reading this string x, right, as long as the space is much shorter than the string x, this string x still has some min entropy. So condition on the configuration here, x has min entropy, and we can apply the extractor to get something that's uniform, even conditioned on the configuration that we reach. Okay, so so this is what I said. With high probability, the distribution of this x conditioned on reaching some configuration is quite large. And that's the basic idea. We can use several independent y's and some recursion. And we showed that actually, if you want to fool space S machines, you only need order S random bits, as long as your algorithm uses a polynomial in S number of random bits. And actually, there's been some recent work on avoiding the union bound and handling more general sources. Really, the ultimate goal here would be to get a generator that fools. If you think of S equals log n, this corresponds to randomized log space. A randomized log space machine could use a polynomial in n random bits, which is exponential in S. So actually, we could hope to output an exponential number of random bits, and there's been some recent work doing that in some special cases, which I won't go into. OK, so that's using an extractor sort of with the definition, with the most straightforward, using an extractor in the way it was defined. But sometimes it's helpful to look at extractors a little bit differently. Well, one use is for expansion. So here we view it graph-theoretically. Here what I did is we put all possible source outputs on the left. So I'm using capital letters as 2 to the little letters. So there's all possible source outputs here, all possible extractor outputs here. And I connect this, for any source output x, I'm going to have, for each possible seed, there's 2 to the little d possible seeds. I'll connect x. I'll see what the extractor does on x and y, and that will give me some output extractor x and y. And so we're going to get a bipartite graph in this way. So this degree d will be relatively small. Little d is small compared to little n. Right? So little d is, think of little d as logarithmic in little n. So big D will say be polylogarithmic in big N. Okay, so big D is pretty small. So we have a bipartite graph with big left side and small right side. And what the definition of extractor says is that if we pick any set of size at least big K, which is 2 to the little k on the left, if we pick a uniformly random string on the left and pick a uniformly random seed and look at the distribution on the right, we get an almost uniform distribution on the right. So in particular, it's epsilon close to uniform. So in particular, it has to expand to at least 1 minus epsilon fraction of the vertices on the right. I put expansion in quotes because the right side is actually smaller than k typically. Right? We expect big M to be smaller than big K. So it's not exactly increasing the size, but it's increasing the fraction on the right. So it's a type of expansion condition.
So maybe it's better to call it a quasi-randomness condition or something.
Right, but I want to connect it to, actually, now I'll connect it to real expanders. OK. So Avi and I use this to construct expanders which beat the so-called eigenvalue bound. Let me just say a few words about that. OK, this board's. OK, the type of expanders we were interested in were large degree ones in the sense. So what we were interested in, we wanted any 2 sets of size k. So we were interested in graphs on n vertices. We wanted any 2 sets of size k to share an edge. Or equivalently, we wanted for any subset of size at least k, we wanted the number of neighbors to be bigger than n minus k. Because if the number of neighbors were at most n minus k, you could take the k vertices that it missed and s, and those would not share an edge. OK, so this is the condition we wanted. It turns out that such graphs are useful in a variety of applications, sorting and searching in rounds, construction of superconcentrators, and more. OK, so this says right here that basically the degree has to be bigger than n minus k over k, basically n over k. And a random graph comes pretty close to this. So a random graph gives something like n log n over k. It's probably even, this might be n over k. It doesn't matter. This is order n log n over k. But it turns out that if you use the natural way to construct these explicitly would be to look for a graph with small second eigenvalue and use the expander mixing lemma. And if you do that, even if you apply the expander mixing lemma, even graphs with optimal second eigenvalue, you're going to get you get degree actually bigger than half n over k squared. Okay, so in particular, if k is less than root n, this is useless. It says that the degree has to be bigger than n. Okay, so the expander mixing lemma is sort of a square off from optimal. But nevertheless, Avi and I used extractors to show that this is to get n to the little 1 plus little of 1 n divided by k. The little o of 1 depends on the quality of the extractor.
Is that log n necessary, even in the random graphs? I mean, are there graphs for which they achieve n over k for this?
And then log of n over k is what you said.
Yeah, I think it's probably, I think this is probably the bound. I didn't check.
So like,
But
I see.
say that it's a graph, a random graph of edge probability of half. Okay. So then you.
No, my question isn't for random graphs.
No, but
Okay.
it would.
It's, are there graphs which have degree bounds O of n over k, which meet this k condition?
Oh, okay. I
Because
thought you meant.
I mean, otherwise you need the log n and all these sorts of things to even be connected for random graphs, right?
So what I was going to say is if you pick a random graph with edge probability of half, it's connected, but you have, and the degree is n over 2, but you have an independent set of size 2 log n. So there you need the log n, because you could pick, half of the independent, the two halves, split the independent set into 2 halves, and that has no edges. So the k is going to be log n.
right. So yeah, my guess is
So
that.
maybe it didn't answer your question, but
Yeah, my
I
guess
mean,
is
for
that the
random
log
graphs,
is
I would
necessary,
be
but.
surprised if we can't realize that construct, I mean, a question like that, right? But,
Yeah.
You can probably just try like what happens with random sets if you have a degree n over k.
Right, for a lower bound, yeah, you could probably. My guess is that the log is necessary, but I'm not sure. But let's just see how it follows easily from a good extractor.
Little of 1 here, is it?
Well, it's right. So I think with the best known extractors, I think it's like polylog n,
so
or it might be 2 to the polylog log n.
it depends on the loss of these.
Right, it depends on the entropy loss of the extractor as well as the degree. So because we don't have, I think it's actually 2 to the polylog log, but I haven't checked it there. So let me just show how it. Can people see this board? I know this. I guess yeah. So how does this follow easily from extractors? Well, suppose we have a good extractor. Well, as we saw, an extractor, if any set of size k would expand here, in particular, say it reaches at least 2/3 of the vertices here, and the other set also reaches at least 2/3. So they have a common neighbor. Any two sets of size k have a common neighbor. So if we look at paths of length 2, so if we connect any two vertices here, if they have a path of length 2 in this extractor graph, then it will certainly have that property. And we're going to get very small degree. Okay, we have to do something else first. I mean, in the definition of extractor, there's nothing stopping this vertex, say, from being connected to every vertex on the left. So we have to remove high vertices here first. But if we do that, then this will be approximately regular, say within a factor of 2. And the degree will be something like, let's see, if this degree is d, right, so there's n vertices here, m here. So nd equals m, right, so nd is md prime. And the total degree we would get would be something like dd prime, which would be something like nd squared over m. And if we take m to be about k, if we can get m close to k, this is something like nd squared over k. And this is what we were aiming for. So as long as d is pretty small and k is very close to m, we get this bound. But let me just write these parameters so that over here, so the parameters, we have n on the left, m on the right. And then the degree here is d, which is 2 to the little d. And then k, which is 2 to the little k.
The point then is that you need the m to be roughly, so it has to be k times 1 minus little o of 1, and still have the number of bits be order log or close.
Or close, or something small, yeah. Well, right, as long as, actually,
I guess
you
polylog is okay.
right, I guess depends what bound you're going for, yeah. But right, so so we need the degree small and we need k close to m, and those are the two factors. Okay, so there's been a lot of work on this. These are, and right now there's several constructions that are independent, but I didn't write the whole history of these constructions. But existence-wise, the degree just has to be about little n over epsilon squared, or log of big N over epsilon squared. And the output length can be very close to k. There has to be some entropy loss, like 2 log 1 over epsilon, at least for a strong extractor. This is for strong extractors. You can't actually output all k bits, but k minus a little bit. And the leftover hash lemma allows you to output that many bits if you don't mind quite a large degree. So this is pretty old due to Impagliazzo, Levin, Luby, and Bennett, Brassard, Robert had a similar lemma, which gave them the privacy amplification. And then now, if you Guruswamy, Humans, and Vedant say, well, we could have just polynomial degree, which is a logarithmic length seed, and output almost all the entropy. Here, alpha is a positive constant, any positive constant. And if you want to output all the entropy, you can have a slightly bigger seed. So say a log squared n length seed and output all the entropy. And then De Vere, Coparty, Saraf, and Sudan showed how to output, use just a log n bit seed and output 1 minus little o of 1 times k. So I haven't checked if this gives something better there. But yeah, I'm not even sure about, I think it's still 2 to the polylog log in this thing. And for some applications, you actually care about the degree itself. So you want the degree to be linear in n. And then I had a construction if the min entropy is linear in n, and for epsilon a constant, you can output, say, 99% of the entropy. OK, so now let me tell you an alternate view of these extractors. So the definition says to look at the left, look at a set on the left and see how it does on the right. But there's an alternate view where we start on the right and look and see what happens on the left. So now we take some set S on the right. It has some density mu. And now this induces, for every vertex on the left, it induces some estimate mu sub x, which is sort of x's estimate of the density of S. So it's the fraction of x's neighbors that lie in S. And now we could define some set bad sub S, which is the set of x for which its estimate is off by more than epsilon. And by the extractor definition, we know that the set of, okay, so bad S has two parts, those which overestimate and those which underestimate. By the definition of extractors, those which overestimate has size less than k. Because if this had size at least k, we could pick a random element from this set and take a random neighbor, and that would overestimate by more than epsilon, contradicting that the distribution is epsilon close to uniform. So this has size less than k. This has size less than k. So bad S has size less than 2k. Okay, so it's really, so this is a view. Any set S, at most 2k vertices on the left are bad, give bad estimates. And this view is actually equivalent. So if you start out saying for all S, bad S is at most k prime, well, the error, well, now think of taking k prime to k a little bit bigger than k prime, or k prime a little smaller than k. Right? So the error of any set S will be at most the size of bad sub S times 2 to the minus k, because any string has probability at most 2 to the minus k, plus epsilon, because every string here could have error at most epsilon. So this is a bound on the error for any set. And so in particular, the error, if k prime is just a little smaller than k, we get a good bound here. Okay, so this is basically an equivalent way of looking at extractors. For any set S on the right, the number of bad vertices on the left is small. And let's see why this view is useful. Okay, so it's useful in constructing so-called averaging samplers. So in this setting, we want to estimate the mean mu of some function f. Say it maps m bits to the interval 0, 1. So the algorithm our algorithm will be to pick some n-bit string x, and sample f at its neighbors, gamma of x. And output the sample mean. And so the probability of error, okay, so we would just have to, okay, I said bad in terms of 0, 1, and now we have the interval 0, 1, but that doesn't make a difference. So here, the probability of error is right, the probability of error, meaning that, by an error, meaning the estimate is not within epsilon of what we want. The probability of the error is exactly the size of bad f over 2 to the n. So this is exactly what the extractor guarantees. If we use an extractor graph, we know the size of bad sub f is small. And it just pops out what we want. Okay, so in fact, using good extractors, we can sample using just 1 plus alpha times m random bits to get error. Okay, the error in the estimate is 1 over polynomial, but we actually get exponentially small error. There's two errors. There's the error of the estimate, and then there's the okay, so let's just write. So there's two errors. Right, so there's
So it's like a probabilistically approximately correct.
right.
So the epsilon and the delta. The
Right.
epsilon is how far off you want to be from the correct answer, and the delta is the probability that you're not meeting that goal.
Right, exactly. So this is, maybe, okay. So there's the probability that the sample mean differs from mu by at least epsilon should be at most delta. And right, so this, we can take epsilon to be 1 over polynomial, and delta to be actually some small exponential, and just do 1 plus alpha times m. So
this goes in reverse too, right? From what you just said, is that if you've got a good sampler, then you've got that's a way of constructing an extractor.
That's true.
So you can like use expander walks to.
Right, so actually expander walks will give high entropy, extractors for high entropy. Right, so here, right, I was going to mention that. Right, so since random walks on expanders, I was going to mention it later, but I'll mention it now. Right, so since random walks on expanders can give exponentially small error, they do give a form of extractor if the entropy is large enough. Okay, another use of extractors is for error correcting codes. So here, and we'll take a somewhat non-traditional view of codes right now. So we're going to encode a string x by a d with d symbols over a very large alphabet, so m to the d. So each symbol is in 1 through big M. So it's a large alphabet. But it's actually hard to get well, you'll see what we want. So it turns out that the notion that fits in with extractor codes is called list recovery, which is a generalization of list decoding. So in this setup, we take some subset of D cross M. And we look for codes words that have a large agreement with respect to this subset. OK, so in traditional list decoding, we would just have one received word. So we would just want to know whether x1 is a particular symbol, whether x2 is a particular symbol, whether x3 is a particular symbol, et cetera. So that would be some subset of size d. OK. So that would be 1 something. That would be the order pair 1 something, 2 something, up to d something.
You're getting multiple values for what?
That's right. Here we're interested in x1 could take on several possible values. x2 might take on several other possible values. We're interested in any sort of possible test for the code word.
Is S necessarily the Cartesian product of some subset of D and some subset of M?
No, it's an arbitrary sub.
So what you're saying is you send this through this very noisy channel, and in fact, for every position in the code word, you didn't get the whole thing. What you got was some information about that gives you some subset of the possible values that it could have.
Right. You could. Good. Right.
Although, and then even some of those guesses about the subset may be wrong.
Right.
So you're just trying to maximize the number that are right.
Right. Right. So we're just interested in, whether we can get a guess that's a little bit better than random.
Yeah.
Right. So we look at the code words that agree with this subset in just a little bit more than what they should. So this is the density of S plus epsilon times D. And just the previous view of extractors says that the number of code words isn't most the size of bad sub S.
So how does this?
So how? So here the encode. I mean, you just the first part was just defining what kind of code you're talking about. So now you have to talk about how you're using the extractor to define a particular code.
Okay.
So
well, the definition.
Neighbors of, these are the different extracted.
Right. So these, I should have said right. So I'm thinking here we have an extractor graph, and I'm letting the neighbors of x be x1 through xd.
In some order.
In some order. Well, I guess if it's a strong extractor, it comes with an order. Right.
So how much more general is it to allow, for each for each possible index, you might instead give benefits for the different values of the symbols, right?
Right.
So that way it doesn't take just 0 and 1 values. How much harder is it to construct things for this?
Yeah, it's a little hard. It can be harder.
Than this in particular.
Oh, sorry.
list recovery.
If symbols take values,
Yeah.
right. Actually, that's the same. In fact, we deal with,
Okay.
right, that's soft decoding. So
Right, okay.
we actually deal with that in our paper as well. And it turns out that this notion of list decoding is exactly what's needed to get hardcore bits. So, so Russell observed a while ago that getting one hardcore bit is basically a list decoding algorithm. Basically corresponds to a list decoding algorithm. Now, if you want to get many hardcore bits, it turns out that this is the right definition, the list recovery. And codes are very important, are very useful for constructing extractors as well. Yeah, I was going to say, I'll say a bit more about codes later, although I guess, yeah, as usual, time is slipping. But I'll put what I was going to show, actually, the Johnson bound, which is very useful in coding theory, it's important for list decoding, is basically equivalent to the leftover hash lemma, which we think of in extractors. I think it's a cute connection there. Okay, so extractors are also useful in inapproximability. There's been a long line of research using PCP technology to get inapproximability results, culminating in the result of Hofstad that max clique is inapproximable to within n to the 1 minus epsilon for any positive epsilon, assuming that NP doesn't equal ZPP. This is zero error randomized polynomial time, which is RP intersect co-RP. So this is an awesome result. The only minor thing that's a little unsatisfactory is that it'd be nice to have NP not equal P. And there's similar results for chromatic number culminating in Feiga and Killian. Killian's result also n to the 1 minus epsilon here under the same assumption. So what you can do with extractors, in particular the linear degree extractor I mentioned, is de-randomize this theorem. So we can show that these same results hold, assuming only NP not equal P. So it's a cleaner statement.
Was the reduction as in how do extractors appear here?
Okay. Right. Okay, it would take me a minute to explain, I think.
Is it in the sort of amplification step, or?
Yeah, I guess you can think of it just as, right, in PCP you want, basically the size of the clique corresponds to the number of random strings that cause acceptance. Okay, so in one case, if X is in the language, then all the random strings accept, and you have a clique of size 2 to the number of random bits. If the string is not in the language, the clique turns out to be much smaller. And right, so it corresponds to, right, so if you think of that.
You want to take a graph product, but then sparsify so that it doesn't get too big or something?
Right, so that's another, okay. So there's sort of the direct thing where you can look at it as an amplification problem and use it more directly. Then there's de-randomizing the graph products. So Joe and Uri used graph products to show their result. And we get some kind of de-randomized graph product from this.
There was like some follow-up paper that said instead of just saying an epsilon, existential, for any epsilon, having some very slow.
Oh, that's right. So yeah, Subhash Kote had even better results, and we de-randomized those as well. Right, I didn't.
Can I ask a question about the extractor codes? So when you were bounding the size of the bad set, so that's sort of like saying there aren't too many code words around those, and then you also have to have like algorithms for finding all of them too, right?
Right.
So what sorts of extractor constructions or properties sort of imply that you can go from the right to the left-hand side?
Okay, so that's a good question. So extractors give you a bound on the size of the bad set, but they don't give you an efficient way to find it. So as Encore says, you need extractors to have a certain property to find the code words, and there are some. So like Trevisan's extractor allows you to find the code words.
So why do some extractors allow you to find them? I mean, what sort of structural property of their construction is sort of exploited to go from right to left in that way?
Well, it's basically, often the proof allows you, if you look at the proof, it gives you an efficient way to construct it. So if you,
Yeah. But
Because the proof
it's
isn't a
sometimes
contrapositive, or because
it's a little circular in that Trevisan's construction allows you to efficiently find it because it's based on good codes with good algorithms, right?
they use, right, but he uses the Nissan-Wigderson algorithm, which,
So I mean, he uses your guys' work in sort of a contrapositive, way, right? In the sense that, so because you guys already had sort of algorithms for enumerating those sets, that allows you to go right to left, or okay.
So you can view his result as converting less decodable codes to less recovery code.
Same.
If you have less decodable
Because
codes,
you have this kind of stronger,
less recoverable.
less recoverable. Yeah.
yeah, I guess. Okay, and I was going to mention Trevisan here. So let me mention pseudorandom generators. As almost everyone knows, a pseudorandom generator takes a short random seed. It's a deterministic algorithm. It outputs a much longer string, which we hope is random enough for whatever purpose we need. And think of this as fooling polynomial time machines or circuits. And there's two variations here. There's cryptographically secure pseudorandom generators. These run in time less than the adversary. And these exist if and only if one-way functions exist. The pseudorandom generators for de-randomization are slightly weaker in that they're allowed to take slightly more time than the adversary. And these exist if and only if hard functions in some sense exist. So Nissan and Wigderson had a way to get pseudorandom generators from hard functions. So basically, you could think of it as taking two inputs, a random seed and a hard function, and outputting a pseudorandom string with small computational error. Yeah.
What is a hard function? Which notion of hardness is it?
Basically, high circuit complexity.
Okay, and the function itself is sufficiently computable.
Not necessarily.
No.
Okay, what?
That's what makes the combination take longer than so it's not useful for cryptography because the function typically takes a huge amount of time to compute.
Okay, and that's why the PRG also runs longer than the inverse
That's right.
the algorithm that it's trying to be run.
That's right.
Right. So think of it as something that whose circuit complexity is not too much less than its uniform complexity. Right. So, okay. Yeah. So Trevisan noticed a surprising thing that these pseudorandom generators, which live in the computational world, give extractors, which live in the information theoretic world. So, like an extractor takes two inputs, and one of them is also a seed. And what he does is basically view these n bits as a hard function. So intuitively, most functions are hard, so it seems to make intuitive sense that if you just use this as the hard function in the Nissan-Wigderson construction, you might get something. And he shows that, in fact, you do. although the proof, you know, it doesn't use the hardness of this. But I was going to talk about it later, but we'll see. Right, so he sets the extractor x and y to the NW pseudorandom generator on this hard function f. So x is viewed as a hard function f and the seed y. And in fact, it's a bit, you get better bounds if you first encode the function f with an error correcting code, as we were discussing. So here you use an ordinary list decodable code to encode f, and then you get this.
In some sense, that's just using the BF-NW construction rather than the NW construction. And that's really what they're doing.
Oh, that's the,
The
okay.
first step is to go from a worst case hard function to an average case hard function,
Right,
essentially by using an error correcting code.
right, right. Okay, so should give, okay.
It's okay.
And there are some types of seeded extractors that are designed for cryptography, but I won't be discussing those. I gave a talk on non-malleable extractors, which I think is quite interesting. It allows you to deal with privacy amplification with an active adversary. Okay. Okay, so now, actually, this might be a good time for break, or should I go a little further?
How much of your slide presentation?
Yeah,
So you're gonna like do half of
right,
your
right.
slides and then
Right, so
go to the board, is that?
that was the original plan, but I'm thinking, I'm thinking that I might have 15 or 20 minutes here, but maybe it will be longer. I could start and see how it goes.
Okay,
Or-
so it's up to you whenever you feel like a break.
Okay. Okay, let's go a little longer. Okay, so another way around this impossibility result, if you don't like using a seed, so for example in cryptography, often a seed is bad because you don't want to try several possibilities. You really need one thing that works intuitively. So sometimes it's helpful to have a seedless extractor, in which case you need to restrict the type of source. So what kind of sources would admit seedless extractors? Well, it turns out that a lot of classes of sources do. In fact, you just need, as long as there's at most 2 to the, say, 0.9 K sources of min entropy K, they're extractors. And just to compare that to the naive bound, right? So how many sources are there? So with min entropy K, there's basically 2 to the N choose 2 to the K possible sources. And this is, say, most 2 to the N, 2 to the K. Right, so it's doubly exponential, but there's this factor of N here. And so if it's just a little bit, if it's just a little bit smaller, then there's deterministic extractors.
But this is just an existence argument.
This is just an existence argument, right? So constructing them, of course, is often much, much harder.
But so what you're saying is if there are that many sources of min entropy K in your class, then there are deterministic things that work for every source in that class?
That's right,
Okay.
non-explicitly, right? So they just exist. So I want to talk about a few different types of sources. So there are types of algebraic sources. You can define sort of bit fixing, affine independent sources. And there's sources defined through complexity theoretic means. So I want to discuss these. Okay, so let me start with independent sources. Here, here we have, it's what it sounds like. So we're always thinking of one source, but here let's say we divide our one source into two parts, and those two parts are independent. But instead of saying n over 2 bits in each part, I said n bits in each. Although, yeah, this should be a y. So these are two independent sources, each with min entropy k. And can we output a uniform or close to uniform string from these two independent sources? And this has been looked at quite a while. So for existence, you only need two sources of min entropy log n, and you can extract from that. Let's just think about even extracting 1 bit. But the best known two-source extractor is by Bourgain, which just barely beats half, barely beats n over 2. N over 2 follows simply from any Hadamard matrix gives you n over 2. And we barely know how to beat that.
But that you should cite that was the result of Shor and Goldreich way back when, even before extractors were defined.
Well, actually, it's Lindsay's lemma. Lindsay showed that Hadamard matrices have this property. So, but then Shor and Goldreich were the ones who put it into this framework. So then Barak, Rao, Shaltiel, Vigderson showed that they could obtain much smaller min entropy, but it's only a disperser. Meaning, if you think of outputting 1 bit, it's just a non-constant bit. Okay, so that's for 3 sources. The best known is a little bit better than square root and by Lee. And unless you allow uneven length sources, which seems sort of unfair, but if you do, then we can get down to n to the alpha. And in general, if you allow, if you just have min entropy n to the alpha, the best you can do for even length sources is order 1 over alpha. By Rao and Barak et al. Improve the error.
So would, can two-source extractors be used as a primitive to get better other things?
Well, I guess if you,
let's say you have a very good two-source extractor, would you get?
I mean, I don't know how to get anything better than the obvious thing, right? I mean, of course, if you have a 2-source extractor from min entropy k gives you a 3-source extractor from min entropy k, but I don't know how to get less. But I haven't tried that.
So in the original extractor picture, you had this large string of some high min entropy. Then you had some tiny seed. So with a small amount of entropy, actually. So you can imagine, what if you said, well, I'm not going to give you a truly random seed. I'm going to give you a min entropy random seed, but with
Right.
but let's say independent of this.
Right.
To give you a chance.
Right. So,
Could you have some case where you have just a
Yeah.
little bit of 2 independent sources, one with just a little bit of min entropy, or they're balanced against?
yeah. So in fact, Ron Raz looked at that question. He showed that you could have an extractor with, if the seed has min entropy rate bigger than half, you still get extractors. But if the entropy rate's less than half, then nothing's known as far as I know. Actually, maybe this is a good point for a break. Yes, let's take a 5-minute break. Yeah.
And so resume at 11:40.
Okay. There he is. Okay, good. Okay, so one use of these extractors for independent sources is cryptography. So there's a natural model. We could have cryptography with weak sources. Here, each player has an independent weak source. And here we'll allow Byzantine faults. For 2 players, many things are impossible. So it's impossible to encrypt, for one person just to encrypt if they just have one source, you can't really do much. But it turns out that for more players, this is possible. So there's something called network extractor protocols, which basically they allow you to start with weak randomness and end up with high quality randomness. So in other words, after an network extractor protocol, most of the honest players end up with good private randomness. And once they end up with good private randomness, they can just run a standard protocol for, say, Byzantine agreement. And these network extractor protocols use independent source extractors. So like a naive idea would just be, let's say we have a C source extractor. Maybe we have C-1 players broadcast their sources, and everyone applies, they have their own source, so they use those C-1 in their own sources to try to extract, something like that. Of course, this doesn't work. Oh, right, to those sources in their own source. This doesn't work. There could be, what if the only players who broadcast are malicious? But then there are some clever things you.
Wait, what if a single person is malicious?
Right. So even if the players aren't malicious at this point, is it clear that this works? Because if you...
Yeah, because you can extract from all the weak sources of the broadcasting players, you can extract a little bit of randomness, and then you can use that as a seed to extract using your private weak source. And the seed that you got.
Do you need like strong extraction?
Yeah, so you need some strong extraction. Yeah, I should say.
Yeah.
Well, what I'm saying there is that these constant source are stated is that you have C independent sources, each of which have certain level of entropy. So what I'm saying is that what if one malicious player broadcast? What if one out of C-1 people, what if one of them is malicious?
Mm-hmm.
Isn't that enough
to ruin it? Right. So you'd want. It turns out.
One of these multiple source extractors that can extract if even half the sources have randomness. So it's not unbelievable that you could get something like this.
Right. So you can hope for something like that, and it can get complicated. You end up. Well, I wasn't planning to really go into these constructions, but I was going to just trying to show that they're relevant, and it turns out that so in the information theoretic setting, you only need even just some relatively weak lower bound on the min entropy, and you can still tolerate a linear number of faults in Byzantine agreement and leader election. And in the computational setting, so you need some certain cryptographic assumptions, which are pretty strong. So they might be something like one-way permutations exist even if the input to the one-way permutation is a weak source, something like that. But under these assumptions, if you believe them, then you can get secure multi-party computation if there's just two honest players. And actually, these computational assumptions allow you to get a two-source extractor, so it's almost so it's going in the opposite direction here. Okay, so another model of where a seedless extractor is useful is a very simple one: oblivious bit fixing sources. So here, so the question mark denotes the uniform distribution on 0, 1. So here, an adversary first fixes all but k bits, and then the remaining k bits are chosen uniformly at random. So for example, parity would extract 1 bit because there's no dependencies. But how do you extract more? Well, it turns if k is at least polylog n, then Gabizan, Raz, and Chaltiel showed how to extract almost all the almost all the bits. And there's an application here to exposure-resilient cryptography. So here, normally cryptography requires the secret key to be perfectly secret. Here, what if an adversary learns many bits of the secret key? Well, it turns out you could still do cryptography if you have something like this. And actually, Rao improved the errors so that this is good enough for this application.
We have one question. Sorry about this. That when the n-k bits are fixed by the adversary, is the adversary allowed to choose after seeing the bits?
No, so the adversary chooses the bits first.
That's what makes it oblivious.
That's what makes it oblivious, right?
So adaptive would be the other way around.
Right. If the
No,
right,
otherwise it would be a general case source, essentially, right? Or
no, not a general case source,
You still
because
have, you
oh,
still have like
Qubits are
randomness and stuff.
okay, all right.
right.
So
So
probabilistically there exist extractors even for adaptive bit fixing sources.
right, because there aren't too many. Well, actually, no, they're not that. Wait. No. I mean, certainly with some very high entropy, but I don't.
For adaptive bit fixing sources, there's like this 2-bit question. It was,
The
so
two-
that was this paper of Shore, Goldreich, Hastad,
And 3 others.
Gold,
That was this.
Gold, so, yeah.
That was the
British is
oblivious.
one
That was
key.
the
Joel
oblivious.
Friedman.
That was the oblivious source.
Those were-
Yeah. So they showed. So that there's a 6-author paper that Russell mentioned. I don't know if I should try to get through all the names, but they showed how to use error correcting codes to get to extract from such sources, but they were interested in extracting exactly uniform bits, and there's actually some lower bounds preventing you from extracting all of that. So then Camp and I showed how to extract if the min entropy is like root n, and then Gabizon, Raz, Chaltiel improved our construction. Okay, so a generalization of an oblivious bit fixing source is an affine source. So here X is a random element from some affine subspace. So obviously these generalize oblivious bit fixing sources. And the best known here is Borgana gave an extractor for min entropy any constant times n. And I forgot to, Bensasson and Koparty gave a 1-bit disperser if the min entropy is like n to the 4/5. Actually, and over large fields, Gabizon and Raj showed how to do it for any k.
There's also an improvement by Chaltiel on the disperser.
Oh, yeah, I forgot. Oops. Yeah, my mistake. Right, Chaltiel showed how to get a disperser, I guess, for any n to the alpha.
Like 2 to the
Or was it?
log to the 1 minus epsilon.
Yeah, so even less than n to the alpha, right? Yeah, thank you. I don't know why. Okay, I left. This is an old. Okay. Okay, so another variation is to impose some say the complexity of the source should not be too large. So here we have the source being the f applied to the uniform distribution, where f has low complexity. Trevisan and Vadan showed that deterministic extraction is possible under some very strong assumptions, like involving several levels of the higher about circuits within the polynomial hierarchy. I forgot now exactly, but it was quite strong, non-standard.
I mean, again, it's sort of like with the pseudorandom generators. So the question is whether you want an extractor that works in time much less than the complexity of f, or an extractor that works with complexity not much more than the complexity of f.
Right. Here they were allowing it to use
Be a
not
little bit more.
a little bit more. Right.
I think there was a reason why you can't do it with.
Right. I think they had a lower bound saying if it didn't use.
And you can use its own, you can build a source based on that function.
Right. Although it seems like, yeah. So you could ask what you could do with no assumptions. Well, here you need some lower bounds. So the best, so Viola has an extractor that handles AC0 sources. And the proofs of these extractors reduce to low-weight affine extractors. So they don't, so they're not really new extractors, but new uses for old extractors. So instead of limiting the time, you could also limit the space. So here we're going to have a min-entropy k-source generated by a small width branching program. So we have, here's our branching program. There's some probabilities on the edges. So with probability half, we took this edge and we output 1. With probability 0.8, we took this edge and we output 1. We took that edge, output 0, et cetera. And the question is, can we extract from such sources? So these also generalize oblivious bit fixing sources. In fact, bit fixing sources can be modeled by space 0 sources. So here's a space 0 source that models this bit fixing, oblivious bit fixing source. And Camp Rao, Vedant, and I showed that basically for linear min-entropy, and if the space is a small enough linear space significantly smaller than the min-entropy, then we can extract from that. And the proof reduces to some variance of independent sources. Basically, if you condition on an intermediate vertex, all the source before that vertex and the source after that vertex are independent. So that's the initial idea. That doesn't give you these results right away. You have to do some more work. But that's the initial idea. Okay, so in conclusion, I hope I've tried to show that extractors are fundamental, and they tie in with a variety of different areas: cryptography, expanders, coding theory, inapproximability, and pseudorandom generators. And I didn't have time to cover all the applications. So for cryptography, there's a slew of applications where I started listing a few. And so some open questions. For seeded extractors, can we get an extractor that requires linear degree for any min-entropy? Right now, we just know a linear degree extractor for linear min-entropy. And can we get a logarithmic seed to extract basically all the entropy? Now, if we want to extract all the entropy, we need log squared n random bits, a log squared n bit seed. For seedless extractors, the big open questions here are to improve the two-source extractor. So right now, we're just a little bit below half. Can we improve that at all, say, to any constant, or any n to that? There's no reason it can't be a lot better, but I don't know. Affine extractors, can we get that for entropy n to the alpha? And also, it's interesting to get other general models where we have extraction. And well, I didn't discuss this, but basically the bounds here are the same now as the two-source extractors, so we have that 0.499 bottleneck. We'd like to beat that. And it's always interesting to give other applications of extractors and show other connections to fundamental objects. Okay, so I think that's all for the PowerPoint part. Now I can use.
You know how to turn it up?
Okay, so I guess hi. I'm ready to. Thanks.
So with the purely transport do they have any useful information before that it just poisons the construction?
Right. I mean.
If they one bit of mutual entropy, would that be enough too?
Right. Well, if that one bit happened to be the output of the extractor, then that would poison it. So you need to somehow define it in some way where it's possible. Yeah, I don't know. Okay. Okay. Well, now we have some choices. Okay, so what I had planned to talk about were the connection with the leftover hash lemma and the Johnson bound, Trevisan's extractor, the linear degree extractor, and the Guruswamy-Uman's Vedana extractor. But that's too much for right now. But I think so.
So does anyone have a suggestion where?
Yep.
Anyone have something they'd like to see?
Yeah.
Probably would be good to see, at least one construction in detail now that we've.
Suggest the GUV one. That's at least my vote.
Yeah, I would love that to talk to.
Okay. Okay. So that's okay. So, yeah. Okay, so what they really do, their extractors really comes in two parts, and they really only do the first part. Well, they do the second part, but really okay, so you start with an n-bit source. Right, this has some min entropy k. There's sort of k bits of min entropy here. And what they first do is they build a condenser. So what a condenser does, it also takes a seed, say log n bits, and it will output another source with min entropy. The min entropy of this other source will also be very close to k, but it will be much smaller. So think of n prime smaller than n. So n, and then you can apply a high entropy extractor. Here. Okay. So for this part, for now, you could think about random walks on expanders, although that doesn't really get the parameters that you want. So that's one option, but then they can use some old ideas to do this part. But really, the main novelty of their construction is in the condenser. Okay, so let's talk about the condenser.
So I think you haven't defined what a condenser is yet.
Right. So
say that the min entropy of the output, you mean for almost all seeds, or?
That's right. Yeah, you're right. It's not exactly the min entropy, so it's close to. Right. So. Right. So the output. So the condenser output should be epsilon close to a source with min entropy. K prime. Well, K prime is about.
On most seeds, right? Is it strong or weak?
It is strong, although I mean, for if you're just okay, if you want the.
If you just want an extractor rather than a strong extractor, it
Then-
doesn't matter.
Then it doesn't matter because the seed is only log n bits, so it won't. Yeah. So let's not worry about that
Okay.
for simplicity.
So then you can think of it as a sort of construction from distributions to distributions, and it should preserve approximately min entropy.
Right. Right. And so we can. Right. Okay. So what they do. Okay. So what's the construction? They view. Okay. So there's the weak source. The weak source they view as a polynomial. Let's say it's from. Let me see. So I think they will just. Sorry. So let's rename. Okay, so it takes n log q bits to describe a polynomial of degree less than n. So let's rename. The weak source length is n log q. So this is the weak source, and the seed. The seed is just some y in fq. Okay, so the seed is just a log n bit string. So what are some natural things to try?
Sorry, can you explain this? What you mean that this polynomial is the weak source?
Okay, so the polynomial. So okay. So let's say the weak source has n log q bits.
So this is the output of the.
Output of the
You
weak.
take the output of the weak source, and you identify it with a polynomial. So perhaps you break it up into groups of log q, and you just use each set of log q bits as the coefficient of one of the powers.
Okay.
Okay, okay, so it could be natural to just try to use a code here, like say the Reed-Solomon code. You could try to evaluate the polynomial on a bunch of choices for y, and it's not known how to make that work exactly well, almost. But what they do is they define some related polynomials, and so the extractor, okay, is going to take f and y, and it's going to output a vector which is f of y, say f1 of y. Okay, so the FIs are going to be related polynomials. So I need to tell you what these FIs are. Okay, and the way they're defined is, okay, they work over an extension field. So what they do is they pick an irreducible polynomial. E of y of degree And then they're going to work over okay, so they're working over an extension field of fq, right? So they're modding out by this polynomial of degree n. So they define fi as f to the h to the I in f. So let's say mod e. Right. So these are the related polynomials that they.
What is h?
All right. So h is a parameter. So for some parameter h. Okay. So we'll see how to choose that. Okay. So that's and I shouldn't write extractor. I should write condenser. Okay. So. Okay. So. Okay, so what do we want to show? Okay. Okay, we're basically trying to show some expansion property here. We're trying to show a condenser. Think of a condenser. We start with some set of size k. Think of it that we want to show that they actually show it's a lossless condenser. So in the sense, if this has degree d, they want to show that the size of this set is something like, right, very close to dk, not d minus a little bit times k. So this would correspond. This is another way of viewing a condenser as a type of expander. So another way to think about this is to say,
Look at the non-neighbors of any set of size dk, and it should be less than k.
right. We'll look at the set of the vertices whose neighborhood lies entirely within this set. Right?
Within the complement of the set? So you want to look at the set M?
No, I think, let's see. No, I think we want to look at, so what I'm saying is that if you take any set, okay, so smaller than this, let's say, okay, this expands to ak. So this should be at least ak, where a should be approximately d. And so now we're going to do it the other. We're going to take the other view. We're going to say, well, let's start with a set S. So S should have size. Have size less than ak. And now we look at the set of bad. We're going to have some set bad sub S, where bad S is a set of X, such that all neighbors of X lie inside S. And we want to show that bad S is less than K. Right? Because this will mean that if we start with any set of size bigger than size at least K, the neighbors will have at least AK. Size AK. Okay, good. Okay, so this is what we want to show, right? So for any S, so we're going to fix S of size less than AK. And now, okay. Okay, so now we're gonna do something sort of, if you're familiar with the Reed-Solomon list decoding algorithms of Sudan and let's say Sudan, it's connected with that. So we're going to define. So we'll define. Well, first of all, S is a subset of FQ to the M. So we're going to define some polynomial Q on M variables, which vanishes on S. And it's non-zero. It's a non-zero polynomial that vanishes on S. So we'll have to make sure that the number of coefficients, how do we know? We'll know that such a polynomial exists because we'll make sure that the number of coefficients should be bigger than the size of S. Okay. Tight. Okay, and
so you're thinking of S as a subset of the extension field, and thinking of the members of the extension field as vectors over the original field.
I'm not yet thinking of it in the extension field. I'm just thinking of it as a vector over the base field.
Okay.
Yeah.
Okay.
So just think of it as a vector over the base field.
Right. Sorry.
Okay. And now, now suppose that F is in bad sub S. So our goal is to show that there aren't too many choices for F.
So then Q of F, F1, and so on is 0.
I guess I did. Yeah, F0. F minus. Let's say F0 is F. This is 0 for every y in FQ. This means that this is, so viewed as a polynomial, this is identically 0. As long as, if the degree, so we'll close. If okay, so we'll need to ensure some of these things here. And now, well, now let's look at the extension field. Okay, so now we claim that right? Because we could, because this polynomial is identically 0, and each of these, f to the h is congruent to f1 mod e. F to the h squared is congruent to f2 mod e, etc. Okay, so this means, so therefore, f of y is a 0 of, say, q star of z, which is and therefore the number of possibilities for f is at most the degree of q star. I should say q star is not identically 0. Okay. So, okay. Well, first of all, so we want to say that q star is not identically 0. We can say that because, okay, here it was possible that that E, we can assume that E does not divide Q because E is if E did divide Q, we could just divide out by E. E is irreducible. It doesn't have any roots. So, so multiplying by E doesn't help zero out anything. So we can always divide through by E until Q is not divisible by E. And we also should make sure that the degree of Q is less than H. If the degree of Q were, say, equal to H, we could have, we don't want to have something like this variable minus this variable to the H. We could zero it out. As long as the degree of Q is less than H, then all the monomials in Q will correspond to distinct monomials in Q star. So basically, this degree will end up being less than h to the m.
So in other words, if the degree of Q is less than h, then all the monomials, all the monomials that were distinct are still distinct.
Right.
So you can just look at the, you had like a monomial in Z1 through Zn, but if you look at the powers of Z base h, they read off what the monomial was.
Right.
The original corresponding monomial.
Right.
So you don't get any cancellation. So Q of Z is non-zero because Q of Z1 through Zm is non-zero.
Right.
It seems that it's enough that all the degrees, each variable in Q has degree at most h.
Right. Sorry. Yeah, that's what I meant.
Yeah.
Right. Yeah.
So the maximum.
Yeah. Right. So is that what I meant? Yeah. I think. Right. Yeah. Degree.
Yes. The degree of, I think it's usually the other one was called total degree. So
Right. So the individual degree. Yeah. I think that's what they did to get. Right. So right, and in fact that, yeah. So just to do the degree bound here, right? So this is at most right, the degree in each variable is less than h, so it's the total degree of q stars in most h minus 1 plus h minus 1 times h plus h minus 1. H squared. Right. H to the m minus 1, which is equal to h to the m minus 1. Okay, so what this shows, okay, so it's kind of a little mysterious, but what it shows is that the number of f that lie entirely, the number of f in bad sub s is, so this shows that the bad sub s is less than h to the m. So this will be the value of k that we're interested in. And so then we just need to show that the number of coefficients, there are enough coefficients, and that's, it's probably not worth going into the calculations. But this is the idea of the proof. Well, it's the proof.
What do you actually get as far as the extractor?
Right, so the condenser, right, so it's a lossless, so they show a lossless condenser, and yeah, I forgot, I should have written down the length of the output, because right, so depending on, I forgot the, I think they end up with an output length that's something like linear in K. So I think, sorry, I should have written that down. But n prime is something like linear in K. Maybe, I forgot, but I wanted to show the idea of the construction. Okay. Yeah. Okay. Well, are there any other questions? It's probably about.
Is there a more kind of black box connection to it's like it's based on the list decoding codes? Right? Is there a more black box connection, or is it very specific for this particular list decoding code?
Yeah, I don't know a black box connection, but yeah, that's a good question. Because the parameters are a little different in the sense that to get the good list decodable codes, right, basically the output size of the code is going to be something like m times the alphabet, right, the alphabet size of the code is like q to the m of the corresponding code. So in the coding, so from the coding theory perspective, you're interested in smaller outputs, smaller alphabets. So you'd want m to be small. But from the condenser point of view, well, we still want m small, but m is much larger than what it would be in the coding theory setting. So that's right. So like a Reed-Solomon code, you would just have f of y in a sense, and so it's sort of an orthogonal direction, I think. Are there any other questions?